in the room has heard of ADLink? Wow, that's a little bit better than I thought. When I was acquired by ADLink about 7 years ago, I really hadn't heard a whole lot about ADLink. So I'm just going to take a moment to go through some high-level information about the company. So what does ADLink do? There's some pictures up there that kind of talk a little bit about what we do. We create application-ready intelligent platforms. But what does that mean? Do you remember for years the market would go out and they'd buy a piece of something here and a piece of something there, memory, computing boards, etc. Then they'd try to put it all together themselves and they'd cross their fingers and hope it worked. Not easy. And then when it didn't work, who would they go to? What throat would they choke? They didn't have one. So for years, we have been moving towards application-ready intelligent platforms. And the individuals that you see in the room here today and what we're presenting today is the example of that. The partnerships between Intel, IBM, PrismTech, and ADLink. PrismTech becoming a member of our family last December was a very, very critical piece of that. So our application-ready intelligent platforms are robust, reliable, and ready. We like the ready piece. Walk into a customer and an opportunity with hardware already loaded with software and firmware, ready for the customer to put the application on, the easy button. These application-ready platforms, we have a wide variety of them, and they're also really designed for very extreme, rugged types of applications. Okay, so a little bit more about who is ADLink. We are actually the second largest IPC vendor in Taiwan. In the United States, about 40% of the business globally is handled here. We have research, development, manufacturing, sales, and service centers in the Americas, in Europe, in Taiwan, and in China, with several other sales centers globally. About 1,600 employees, and a very, very, very high focus on standards and technologies. So where do we sell that? Who do we sell that to? Here's a sampling of just the customers in the Americas. And I think if you look at the logos that you will see on this slide, it's a who's who across many different verticals. So with that being said, I'd like to turn it over to Toby and we'll get into more of the details. Thank you very much.
Okay, so we're going to start out, I know that Rob and didn't want to define what IoT was, and Brian kind of alluded to what it is, but I think we need to basically recap what has been said in the first two presentations and actually look at what IoT is about, and that will lead us into Jeff's presentation and finally Rob, where we get closer and closer and closer to actually seeing something in action, an IoT system delivering value at the edge, making decisions at the edge. So when I think about IoT and when we've been working on these projects together with the ecosystem, it's really about turning data into information so that we can make decisions on that and act on it. Okay? And how do we do that? Well, you've got the things, and we've heard about collecting data and collecting data for the sake of collecting data, but it's more than that. It's observing the physical world, bringing in data and orienting by bringing in data, for example, with IBM and the Weather Channel acquisition, that data, bringing that data in to bring that together in order to be able to make decisions that we can act on. And there's constant feedback loops in there guiding things, and you're constantly improving things. As Brian mentioned, what you deploy today is probably not going to be what you need 1 year, 2 years from now. So you need to constantly have a platform and an ecosystem that you can constantly be improving these things. So this is the framework that we're sort of working in when we're talking about IoT. in this context. And one of the things, this is a diagram from Deloitte that talks about the information value loop and how you derive value from the data that's coming from that physical or virtual world and turn that into intelligence and eventually augmented behavior. But what I want to focus on is the information value drivers. What drives the value of that data or that information that you get out of it? And there's three things that they pick out when they wrote this article. The first being magnitude. So the scale, scope, and frequency of the data. These are all important things that you need to consider with the data when you're actually building one of these systems. How relevant is that? How is that going to drive the value that I'm getting out of my data? The risk, so the security. We can get data pretty much out of anything, but how secure do I need that to be? What is the risk that's going to introduce by opening a network connection into my factory or my car? We have to consider that when we're extracting data. The reliability, so as Brian mentioned, driving your car, do you want to be reliable or rely on a connection to the cloud to be able to do that? Do you want to rely on a connectivity technology that could break and that you have no guarantees that it's going to deliver information or data in the time that you need? The accuracy of that data. A lot of people talk about these sensors and their ability to acquire data, but a lot of the time, not every sensor is built equal, and not every application needs the same accuracy of data. And then the time. And I think this is pretty much the driving factor in what I'm going to talk about today. And time, we deal with timeliness. So when is it that I need to use that data in order to extract the most value from it? And then how long do I have in order to make those decisions and work with it? So when is that data most valuable? Well, I like to think of it, most people know about the time value of money, right? A dollar today is worth more than a dollar tomorrow. Well, in a lot of cases, that's the same with data, right? As you get that raw data stream, so my green line here, as that data becomes older and older, in terms of the raw data itself, the value of it diminishes. And what I can do with that data diminishes in a lot of cases. Okay, I'm sure somebody could find an edge case or something that points out that where that's not true. Now, conversely, if you look at aggregated data, so trends in the data and whatnot, the value of that data goes up over time because you get more data points, you get more value, your sample size increases. So this is important to the subject today when we talk about data at the edge. So the next one sort of puts it in context. In a lot of the systems, especially industrial IoT, the biggest amount of value you can get out of the data is in the raw data stream is at the sub-millisecond. And then as you go towards the sub-second, the minutes and whatnot, the types of analytics and the types of things you do with that data changes. Okay? So you can think of the sub-millisecond, that's really where you're interacting. I press on the brake, I expect, if I've got software-defined braking in my car, I expect that to actually stop the car, right? It needs to react to what I do. You're getting data from the pressure on the gas or on the brake pedal, but that needs to react to that data immediately. We don't have seconds or minutes to look at that. And then you go through analyzing the stream, looking for anomalies or patterns, up to analyzing history and doing things. And then at the far right, you have where you get into the data science world, where people are looking to learn from this aggregated data and discover new meaning from the data or new information that they can take, and they can actually take that and close the loop and bring that data back to be able to use it in an interactive manner. And I think when we get to our demonstration at the end, you'll see how we close that loop. So the first thing I'm going to do is talk about the evolution of IoT architectures, which kind of summarizes a lot of what Brian mentioned in his, but we're first going to look at cloud-centric architectures. So a lot of the Amazon IoT, Azure IoT, what is the core of their architecture? It's about connecting a device to the cloud. Maybe it's a gateway, but it's always about sending all of your data to the cloud so that you can analyze it there and make decisions in the cloud and potentially send those decisions back down to the things or a different thing to put that into action. So it's about in-cloud analytics and in-cloud storage. Do everything with your data in the cloud. All the devices is really, or the gateway is really about sending the data to the cloud. Okay? That's how most people today think about IoT architectures. And there's lots of examples of these platforms out there, and some of the biggest platforms. Now, I need to change this slide after the announcement on Tuesday from PTC, but most of these are cloud-centric platforms. Even IBM has a cloud-centric offering when it comes to this. But there's challenges with having cloud-centric architectures, and we're going to look at those. So, you know, an IoT presentation wouldn't be complete without a slide like this, right? Brian had one. I was surprised Rob didn't have one, but you know, Rob likes to disappoint everybody. So you've got your 50 billion devices, and what? There's too many devices to be for those cloud-centric architectures. You know, Brian talked about the network constraint. There's the volume of devices where it's just not feasible to send all that data to the cloud. And the other thing is, in a lot of industrial IoT applications, the cloud-centric architectures, just the assumptions that are made in designing that architecture don't fit with industrial IoT. Okay? And why is that? Well, one, there's sufficient bandwidth. And we've already seen that today. There just isn't sufficient bandwidth. And going forward in the future, this will become a bigger and bigger challenge, is the amount of bandwidth that it takes. Take, for example, am I too far away, Rob? Okay. A smart city, or sorry, a smart factory. And this is actually on the smaller side of the volume of data. You know, they produce 0.5 terabyte of data a day. That's one factory, right? If you consider some of these industrial cities where they have hundreds of factories, think about all that data having to flow to the cloud every day. It's just, you know, we're going to hit the law of physics, and we're not feasibly going to be able to do that. So what's the next one? Well, the next one is everybody assumes that you will always have a connection, and that's not an issue. There'll never be a break in connectivity, or if I lose it, it's not a big deal. But there's a lot of situations where you need your system to run and continue to get the value out of your data, even if your connection to the cloud breaks. Take, for example, you know, we've done a project with some large agricultural vehicle manufacturers where in the far corners of their fields, they just have no network access. But those vehicles still need to function, right? So they need to be autonomous at the edge without a cloud connection. The third one is latency. You know, we've already had an example of this, so I won't spend too much time on it. But when you are using, you know, you're driving a car and you need the cloud to make a decision for you in your car that in the sub-millisecond, you know, you can't afford the latencies of cloud connections. Think of, you know, a car manufacturer who's using KUKA robots to build cars in a completely automated fashion. Does it make sense? Or can they afford those sub-millisecond decisions to be made in the cloud? No. And then the fourth, the cost of connectivity is negligible. The latest report that I read is on the low side, you're looking at $1 per device per month for a lot of the things that are require a SIM card in them. That gets really expensive when you have millions of devices. So you've got to derive an awful lot of value out of your data in order to justify the cost of that $1 per month. You know, think of the smart grid. There's, you know, hundreds of millions of devices and sensors sending data from remote locations that don't necessarily have Ethernet connectivity or LAN connectivity. That have to go over 2G, 3G, 4G networks. And the fifth one, and I think this is most important, especially today, as the industry evolves, is that people are comfortable exposing their data to the cloud. There's still a lot of, and especially in the industrial context, they view their data as part of their core competence or their core value, and they don't want to share that. They fear by giving that to Google or to Amazon that they're going to lose part of their competitive advantage. So we looked at cloud-centric architectures and seen, why they're not necessarily a fit for all situations. So the next evolution is an edge-centric architecture. And that's what we're here to talk about today. But edge-centric architectures themselves, what are they? They're bringing elastic compute, all the features you have in the cloud, to the edge. That's the way we view an edge-centric architecture, okay? So just imagine the cloud and you bring it closer to the edge. It's going to be a reduced scale, but you've got elastic compute, you've got elastic storage, and you've got elastic networking, okay? But this comes with some, and there's already some platforms that are starting to appear on the market, and they come in different forms and names. Some of them are fog platforms. Other people call them mobile edge computing. But they're all in this sort of the same family of bringing those cloud capabilities closer to the edge. But again, the edge comes with a different set of challenges. So what do we have to consider when we're looking at the edge? The environment. So when you're sending data to the cloud, right? You've got a data center that's it's a nice air-conditioned building and whatnot. Well, when you're deploying these systems at the edge, it's not as serene as Tahoe, okay? You're going into, these things could be deployed in the Arctic, the Antarctic, the Sahara Desert. They could be deployed on factory floors with a huge amount of dust. So you have to take these things into consideration, that it's not a data center environment. The second one is security. In a data center, your surface of attack is fairly well known, right? You have controlled access to the device. Well, if you deploy this in a field, let's say it's a smart agriculture, and you've deployed this into a farm field, and just throw the device out there, well, you don't really throw it, but it's left out there, and at night, you don't know who has access to your field. They have physical access to the device, which poses a whole new set of security challenges, increases the surface of attack for security. So that has to be considered as well. Take, for example, I think one of the best known cases is Stuxnet, where this wasn't connected. This wasn't even a network connected situation. It was done by a USB. So they had physical access to the system, and they were able to introduce the virus. The next one, and it's well documented, I think, in the IoT world, is power, right? A lot of these devices are going to have to operate on batteries or solar power for months, and in a lot of cases, years. So they have to be built in a power-conscious manner. Power is not free in a lot of these cases at the edge. One of the biggest challenges we face on a day-to-day basis in building these systems and talking to customers is every single one of them we go into has a different protocol or a different device they're connecting to, right? In the IT world, it's become pretty standardized what you're connecting to. Well, if you consider every customer, we're dealing with things like this, and this is only a small subset of the protocols, and this doesn't even include the devices that a lot of those protocols are connected to. So if you take Modbus, for example, it's fine to support Modbus connectivity, but what's at the end of that connection? What does the data mean that's coming off that device? Every device connected by Modbus is not the same, okay? So this introduces a whole level of complexity that you must deal with at the edge. And I think, and the final challenge is cost sensitivity, and Brian mentioned that earlier as well. A lot of these devices have the potential to be disposable, They will never be recovered. They'll be deployed. People won't come back to retrieve them, and that puts downward pressure on the cost of these devices. So what's the answer? Anybody have a guess? 42. No. But, so that maybe, but that doesn't really help us. So I'm going to invite Jeff up to actually give us an answer of how we can address these challenges at the edge and what the best approach to do that is.
Thanks, Toby. I don't know about 42, but 30 is a bad number. Especially if you're watching the Warriors game last night, 30 was a terrible number. But we've set the stage so far. We had Rob ate apples, but Brian talked a little bit about the evolution of the internet and that first phase, connecting the unconnected, and that's one of the things that we want to look at here. All right, computing at the edge. So if you're going to do computing at the edge, the obvious thing that you're going to need is a computer at the edge. And when we look at connecting those unconnected devices, those devices by very nature being unconnected are not likely to have a compute engine there, or if there is one there, it's probably doing something. And the last thing you want to do is interrupt that function to be able to put it on the edge so that you can monitor it. So when we look at computing on the edge, we need to look at what can we put on the edge that can be used to monitor that device so that you can respond to the information. So what do you need if you're going to put something on the edge? What are the characteristics of a computer that you're going to put on the edge? As we heard from Toby, things that are the edge can be a harsh environment. So a small form factor, that's important for something on the edge. Being able to work in harsh environments, right? That's important for something that you're going to put on the edge. Something that is reliable. And if you're putting something on an edge device and your goal there is to monitor that device, that computer needs to be reliable. The last thing you want to have is reliability issues with something whose job it is to determine the overall reliability of that edge device, right? And ready to go. That may not be obvious when you look at a lot of the pieces we've talked about today, whether they be the software components or hardware components. Integrating those pieces together and being able to perform these kinds of actions is not something that is a shrink wrap, out of the box, turnkey kind of experience. When you look at what it takes to put some of the stuff together, and we'll look at the conveyor demo here in a little bit, but as Toby talked about, you've got to connect to sensors that are on the southbound side of the gateway. And connecting to those sensors, that may sound not that difficult. As Toby said, you could have a Modbus connection, maybe a Profibus connection, or something along those lines, but you've got to define that data up to the computer and up to the cloud so that it can be acted upon, right? The data itself needs to be defined. It may need to be normalized. It needs to be identified so that it can be acted upon. And a part of being ready to go is an environment that allows you to be able to configure that data so that it can be used. Otherwise, that data is not of much value if you can get it into your box, but you're really not able to use it. The northbound connectivity is relatively straightforward, right? The internet or some kind of 3G or some type of LTE connection to be able to get to other northbound. And then east-west connectivity, we haven't talked too much about that. There's a lot of focus these days about north-south, right? The south going to the I/O, talking to the I/O, northbound pushing it to the cloud, but what about the side-to-side? Other devices that may need access to that information that are local in the same proximity, right? So something side to side that might want to share the information. So here's an example of what a potential solution might look like. It's hard to tell from a PowerPoint what that looks like. You'll see some of it up here as well. But here's a box, a relatively small box. It's our matrix box. It's an Atom-based processor. And that is something that we would look at as something that can be used on the edge. There's a lot of different southbound connectivity options. Some of that is hardware, some of that software, but usually a mix of the two to be able to talk to your southbound devices. Reliability, so low power, fanless operation, those kinds of things are important for a compute engine if you want it to be long-term reliable and robust and powerful. So here's an an example of something that could be used on the edge if you're looking to be able to collect data, maybe do some control on the edge. But sometimes the edge device, and it being atom-based, may not be sufficient. So there are certainly other options. And one thing I'll certainly acknowledge, because a lot of the stuff that we're talking about today is in its infancy, how things get partitioned, where are the controls being done, where the scoring's being done, where the loop's being closed, that can shift depending on the application. You know, there's some applications where we talk to customers and an atom-based processor is more than enough for what they're looking for. It's kind of surprising to me personally that an atom would be able to run the analytics and close the loop, but in many applications it can. I think it speaks to some of the power of the analytics and the small footprints that are available. But there may be a need for Xeon class processors. And we've got a box back there that's the CETO box here, which has got Xeon class processors. So they're for applications that require more compute power, but still need that same level of robustness and ruggedness. You know, you normally don't think of robust and rugged in Xeon class processors. You're looking at, 45, 50, 55, 60 watts of power. It's a lot of power. And being able to cool those boxes and run them reliably over temperature in harsh environments is not a trivial task. So there's an example of something that can be used in applications that require more horsepower than you might get out of an atom. So, we look at these two boxes as being somewhat of building blocks, things that you can use for certain kinds of applications. And this slide talks to PMQI. PMQ being the predictive software from IBM, and the I there, that lowercase I, is kind of the acknowledgement of the Intel Inside. And we've all seen the Intel Inside ads on our TV. So when you look at the partnership here with IBM, Adlink, and Intel, we're looking at being able to provide all of the pieces that you need to be able to perform those analytics. You've got the PMQ software, you've got the hardware with the Intel Inside, as well as some additional software that Toby will talk to that has to do with some of the data sharing. Because in all the stuff that we've been looking at here, one of the things that's running in the background, but it's very important, is the data, sharing that data. So, Rob, did you want to say anything about the PMQ?
Thanks, Jeff. So as Jeff mentioned, one of the key things in doing or in delivering this platform that enables edge analytics and enables you to extract value from your data at the edge is getting the data to where it needs to be, when it needs to be there, and in the form that it needs to be. And that's where we were acquired, but Vortex or PrismTech was acquired by Adlink to bring that to the application-ready platform, so that you can buy a platform off the shelf to do your edge analytics that has that capability to deliver your data where it needs to be, reliably, on time, with the robustness and the fault tolerance that you need at the edge in these types of systems. And of course, it has security.
What's neat about what we've done with this solution is we've taken the power of IBM Analytics and we've really done a detailed dive as to where should particular kinds of processing live in the ecosystem of the Internet of Things, in the context of where the value is created. And so what Adlink has done is they are a very significant partner of IBM's and have actually taken our predictive maintenance and quality platform, as well as connections to our Watson Foundation capabilities in Bluemix, and our connectivity for real-time monitoring, as well as adapters into the rest of the APIs for Watson. Those have now been folded into the PMQI appliance. And that appliance is designed to be deployed in a hybrid mode so that not only can we capture data from those little boxes, but we can deploy relevant components of our data mining platforms into harsh environments so that models can be refreshed right in the field. And this has huge implications, for example, in mobile fleets. Some of the examples we deal with, for example, with if I've got a ship, it's not like I can upload a terabyte of data a day while I'm out in the ocean. My satellite fees are going to kill me. But I have to reprocess models about all of the equipment that's running on that on a regular basis. looking at the aggregate data, applying new machine learning algorithms, and that's the kind of thing that can happen. I definitely take a look at that CTO box later because, I mean, literally that thing's bulletproof. And the application in those particular cases for really harsh environments is interesting. So, again, PMQ enabled, IBM enhanced solution, pretty exciting. I'm actually going to let Jeff here talk about what this is designed for and
Right, so here we'll give you a couple of real live examples of PMQ, that is things that have, problems that have been actually solved and PMQ systems that have been deployed. So in this example, this was actually in an Intel fab facility. Intel was interested in being able to determine the health of their chillers. Chillers that are the things that cool the water that are used in everything from air conditioning to the fab process.
This particular, off the conveyor. In a real world use case, the purpose of an autonomous conveyor is, the shop floor is running, and just like all the equipment on the shop floor is running, and if we get to a point where something's going to break, what do we have to do? We have to stop the line. That's a very bad thing. So it's better for us to perpetuate and let the system potentially even just run a little slower in a stressful situation, so that, I think you got to actually hit this vibration sensor. There you go. In those particular situations, the conveyor slows down automatically. Now, how's it doing that? There are predictive algorithms running, machine learning algorithms. We built them, and now they're running on that box, and they continue to learn about the stresses on this environment. So each of the different sensors, why don't you put some weight on that thing? And you can see here that we have different kinds of stress points that we can introduce, which will adjust the different speed. And if you hold that down, and Jeff, you flick the little vibration sensor there, we can not only trigger, slowdowns, but if it gets to a really bad situation, we'll actually kick off an emergency stop. So what do you got? What's this basically implying? We have a system here which, in normal SCADA networks, I would configure a set of rules, and all those things would do is do basic stimulus response. In this case, what we have are predictive algorithms running on the device, controlling the system. That's where the value gets created. That's the edge. What's happened is the conveyor company has decided that they want a piece of the maintenance business. So I can sell that for a subscription fee. That's disruption. That's the power of the edge, creating value in new ways. And besides, it's fun to come and whack on this. So when the beers come out, we'll leave this on. You can come and you can see if you can slow it down, see how slow you can get it. If you want, you can also put things on it. I don't encourage you to put a beer on it, but then it's got the little light thing on it, and you can also see some of the other pieces that actually make the sensors connect, because you've got not just the gateway, but you've got other pieces as well, Jeff, that make this work, right, that are AD-Link technologies?
Correct, data acquisition pieces.
Data acquisition, DA converters, things like that. So, okay, with that, I'm going to try to take this back to this slide set, and I'll let you, or actually I think Toby, I'll let you wrap it up. I think you've got one slide here to wrap it up. Right?
Yes. So.
Well, I thought you had, there it is.
Okay.
Yeah.
So I think the message we wanted to leave you with is that we've showed you that you need to in order to extract data or value from your data, you need to use that data where it makes most sense and where it is most valuable. And through our partnership with Intel and with IBM, we built a ready-made platform which will enable you to actually do this. It's got the integrations to enable you to extract value at the edge and also to extract value in the cloud by doing your machine learning and your advanced analytics in the cloud, taking the results of that and pushing it back to the edge where you can get the most value out of that.
Thank you very much.
Thank you.